To understand circular motion, all you really need to do is take a look at concepts that we've previously learned and just apply them to a curved circular path. The first thing to realize is that the distance, the total distance traveled by an object that travels in a circle, is just the circumference based on how far that object is from the center radially, how far the radius is from the center of that circular path to the object itself. Now you can find the circumference, which is that total distance traveled, and that just equals pi times the diameter, or 2 pi r, which is the same equation. The important thing to note is that the radius refers to the distance from the center of the circle to an object's location. I understand that that is the basic definition of radius, and you probably are aware of that already. However, I do want to highlight, if this is a spinning disk, let's say, and I have an object located maybe here and one located along the edge, the radius of the circle itself, that disk, is constant, but when we're calculating the distance that each object traveled, well, if one object is here, we don't use this entire radius. The radius refers to the distance from the center to that object. And if we had an object out here on the edge, then the radius would be larger from the center all the way out here. So just be aware that the radius within the distance equation for a specific object has to do not with the radius of maybe the Ferris wheel that the person's on, or the CD in the CD player. If there's a specific point we want to locate, the radius refers to the distance from the center to that specific point. So to show you something a little bit more detailed and to give you the two big key concepts that we have to understand, I've drawn a disk here that rotates counterclockwise, and I have three objects. I have object A, object B, and object C. And you can ignore the colored arrows for right now. I'll explain those in a second. But if you look at A, B, and C, we have C being the closest, A being the next closest, and B being the furthest away, all the way on the outer edge. Therefore, I have three different radii if I want to analyze the situation. I have the radius to object A, the radius to object B, and the radius to object C. And again, that just highlights what I was saying up here. The radius of the disk is constant, even here it is, but the specific distances from the center to the objects I want to analyze is different. Please just be aware of that. Now, the first concept we need to realize, if you think back to that marble and ring demonstration, as soon as the ring was removed, the marble had the ability to travel in a straight line at a fairly constant speed. And the important thing to realize is that's what these objects do. Any object that is spinning in a circle or going through a curve wants nothing more than to go in a straight line. If there's something preventing it from doing that, such as a force, then it will not be able to do that and it will travel in a circle. But it's important to understand that at any given moment, that objects traveling through circular or curved paths, they want to travel straight at a line that is tangent to its current position. So object B here is spinning on the outer edge. If it was right here at this specific moment, that velocity wants to shoot in this direction. If there is nothing else acting on it, it would like to go in this direction. There is something acting on it, so it will continue to curve. But as you can see, A is going in a circle, and as I come into this point, it wants nothing more than to go in this direction. Again, there is a force, so it will curve, and this arrow will be pointing in this direction in a second. When A gets over here, it will be pointing up. As A comes around over here, it will be pointing in this direction. But it's important to understand that this velocity is always tangent, not necessarily to the circle that it's on, but to the circular path that that object is traveling. Same thing with C. Now, because of this, instead of calling it velocity, the velocity experienced by an object traveling in a circle is known as the tangential velocity. And that gives its direction as well. If I were to calculate the tangential velocity of B, it would be X number of meters per second, whatever we found, tangent to its circular path. So it's important to realize that at any given moment, these arrows for each of these objects will always point tangent to the paths that they are currently traveling. Now, if they'd like to go in this straight path, how come they curve? How come they don't do what they want to do? And that comes down to the force that's acting on them. And we'll analyze that much more in depth, and we'll look at what Isaac Newton discovered about them. But the important thing for right now to realize is forces cause things to change their motion. That's basically what they do. So if an object would like to keep going straight and it doesn't, that must be because a force acts on it, a push or a pull. In this case, it's toward the center, and that will cause this object to curve. So not only do you need to realize that the tangential velocity is that velocity that acts at any point during a circular object's motion and wants that object to travel in a straight line tangent to the path, the reason it does not do that is because of the force that acts on those objects, which always points towards the center of the circle or the center of the circular path. And if you think about it, it kind of makes sense. If object B would like to go straight in this direction, but instead of going straight, it curves to the left, well, that must mean that something is pulling it to the left. If object C would like to go down in this direction, but instead continues to curve downwards, there must be a force pulling it kind of downwards. Same thing with A. It would like to go here. It begins to curve up and to the right. Therefore, there must be something pulling it up and to the right. So the two important concepts are tangential velocity and the force that pulls that object towards the center. If I remove that force, that object will travel off in a straight line in a path that is tangent to the circle. If that force is present, that object will continue to travel in a circular path until that force is removed. The last thing we would want to know, instead of conceptually understanding tangential velocity, would be how do we calculate it? And again, I've shown you two examples. We have object A, object B, different radii from the center. At this specific moment, as B travels around, it wants nothing more than to travel in this direction. A, as it travels around, would like nothing more than to travel in this direction. If there's a force acting on these objects, they will not do that. They'll continue to travel in a circle. But how do I find the actual magnitude now that we understand the tangential direction of the velocity? Well, we just have to think to our basic definition of speed or velocity. We'll get into a more in-depth explanation of why I've used the term distance here instead of displacement, but that will come in a future lesson, a future video. For right now, just accept that the basic concept of how fast something's traveling is how far it's gone over a given amount of time. And if we're talking about a circle, the total distance that object gone is just the circumference based on its specific radius. So if I find the circumference, which as we know is either 2 pi r or pi times diameter, either one is acceptable, that's the total distance that this object has traveled. And instead of time, we want the specific period of time that it takes to complete one revolution, which is known as the period. So if I take the distance traveled around the circle for one cycle, and I divide that by the time for one cycle, what I've essentially done is calculated how far it's gone in a certain amount of time. And we usually call this v sub t for tangential velocity. And just remember that if I want the magnitude, I can use this equation, circumference over period, and the velocity always acts tangent to the circular path.